Okay, you can see now MATLAB. And let me repeat just shortly what we did, but very shortly last time. Look here. You defined a regressor. Last time we defined a regressor, but if you remember the lecture, I don't remember in which course, probably not so in optimization. For the bachelor students, we have seen the method, one method to choose a suitable regressor in the course of, I don't remember the title. But anyway, probably you have seen this R square adjusted somewhere in some courses in my program. Let me see. Let me say. In any case, assuming that this is an impossible regressor, how is we consider this at this moment doesn't matter. But of course, we have the possibility to choose a suitable regressor. Just to remember, you R square adjusted is one of the possible methods. Now look at this line 20. Before explaining again the line 20, the regressor here is in a function which depends of x as a set of data. In particular, this is a real project, or at least the first step of a real project, which we tried to estimate, to approximate the roughness of a surface as a function, in this case, of the position. But of course, therefore, I told you is the first step. The idea, if we are considering a surface, the roughness depends on two dimensions. At this moment, just to start, just didactically to show you, we have y Bereknet, which is, or the y in general. If you remember, we have here the data. You can see here y data, x data. Y is exactly the roughness. If you remember, I told you we measured with a glossmeter, and x is in a linear position. Basically, we try to find in a function of x in order to identify y the roughness. Of course, in the whole project, we have a surface. This means we have two dimensions. No? The roughness depends of, let me say, x and y, even though here y represent the roughness. Yeah. Now, the object function we can see here is the least square. You remember I told you last time. This is the least square. This means is the sum of the error squared. Error of what? The error of the corresponding, we can see here. The corresponding element, measured element in terms of roughness using the glossmeter, and the corresponding, again, this is a very important word, the corresponding element of the regressor. Of course, the regressor is unknown. What is the meaning? Is known the structure, because we can choose a possible regressor with different methods. I don't want to go in depth. We will see in the project. But of course, the structure is this exponential form. But what we have to calculate are the parameter x1, let me say, x2, and x3. Of course, we can use also different regressors, I told you. X data are the measurements. Isn't a fitting problem. The last time I told you this isn't really a fitting problem. Now, in this kind of fitting problem, we don't have any, let me say, dynamical element. I mean, the regressor is a static regressor, and the cost function, as basically almost always, is also, excuse me, the regressor is a static regressor, and the cost function, as almost always, is a static cost function too. Now, nevertheless, and we calculate, you remember, x1 and x2 and x3. What happens if the problem is a dynamical problem? I mean, very often, and then I will switch on the lateral camera. The identification problem is more interesting, or better to say, of course, also more interesting, but also more useful in the context of the dynamical system. I mean, if I have a model, a dynamical model, differential equation, and I have to estimate the parameter of the parameters of the differential equation, which characterize the model, of course, it seems to be that this method here is not appropriate, because we don't have any dynamical element. But now I will show you how we can extend, we can nevertheless apply, for instance, PSO or other methods. Now I will sketch how we can apply PSO, and this could be also in a possible initial project for you. Why not? We can discuss what we can do. We did, nevertheless, many projects in this kind of course or in similar courses using PSO to adapt parameter of dynamical models. Again, here we cannot see any, let me say, dynamical systems. Okay, let me now consider a slide in which I will show you a dynamical model. I will try to introduce the discretization of this dynamical model, and then I try to tell you how we can apply. But I don't apply now with MATLAB Simile, but I will tell you how we can apply PSO to estimate parameters of a dynamical model. Here, everything is static. Basically, we speak about the identification of a regressor, which fits, remember, the problem is fits characteristic of a possible dynamical model, But at this moment, the dynamical model is not there. You remember in the course of optimization, I called this method here, which we can see, which we have seen last week using PSO, non-parametric identification, even though x1 and x2, x3 are parameter. Yeah, the reason of this strange nomenclature is that for parametric identification, we intend the parameters of a dynamical model, of a dynamical system in this sense, which basically characterize the parameters, characterize physically the system. I mean, x1 and x2 and x3 are parameter, yeah, but not all parameters are physically relevant in the sense. At least it could be. I do remember, if you remember, in the context of a polynomial, we have seen this. Or yeah, let me say, not necessarily they have a physical meaning. In this case, yes. Now x3 is the roughness. Also, x2 is a roughness, and x1, excuse me, is a roughness. x2, if you remember a little bit math, is meter up to -1. If x data is meter, you remember I told you is in the distance. This means, yeah, x1 and x2 clearly express the output. x2 is something a little bit more abstract. But anyway, just to repeat the nomenclature, let me now introduce a new, let me say, new topic. Why not? But in any case, I try to connect what we did. Second, I try. Yeah. Let me switch on the lateral camera. You can see. Let me. The meantime, look at the system here. Isn't it dynamic? So, now, I hope you can see. Is also I have also the possibility, but I don't know. This is a dynamical system. Yes, we have seen in math. We have seen in math. We have seen also in some of my courses. It's dynamic because we have the derivative of x, which is a state variable, equals an expression which depends on x and y, alpha and beta will tell you, and y is another state. The reason is, and you remember in some of my courses, states are characterized by the derivative y that, because the states or state variables represent or reflect the energy of a system. Now I will tell you about the system a little bit more in depth, what the system represents. Alpha, beta, gamma, delta are parameter to be estimated, Again, the course start with estimation, identification, and then we will move in control, to control a discrete, everything discrete. At this moment, the model which we have is a continuous model, because we can see the derivative, we can see the variable which depends of t, time, which is the independent variable, which is a continuous variable. X, y are continuous variables. About this dynamical model, I would like to say that the model is the name of this model is Lotka-Volterra model. I don't know if you have seen in my course. That is, it's didactically it's important because it's not so extremely difficult to explain, even though the idea is, I don't want to go in really in depth on this, but we can do with some projects. But to control, to identify, and then to control, it's a quite complex system because we don't have the analytical solution of x and y. This means we can just calculate approximation of x and y. We can just simulate. We can just find numerical solutions. But for us, it's enough. No? For us, it's enough. I used very often this model of the system in my lectures because, yeah, I started to tell you the truth. I started with this model, which I knew because this belonged to my when I was young, when I was a student, the professor introduced this model for different reasons. This is the basic model, Lotka-Volterra model, which can describe also very complex nonlinear systems. But again, I reconsidered this model here in the period of the COVID, because basically can be seen with some modification. Probably you have seen the modification, because SIR model, no? SIR can be used to model pandemic situations, COVID, for instance, or any kind of historically we used not exactly this, but an easy variation of it was used to model, to predict, to control, control through vaccinations and so on, also different pandemic situations. But let me go ahead mathematically. At the beginning, I would like to try to explain how we can use PSO in this context here, and why not? We can also conceive in a possible project. We already did I think, 2 or 3 projects with different, of course, insights, with different issues, is applying PSO to SIR. Also here, I think, in this kind of equation. Okay, first of all, again, x and y are the states and variable which appear in their differentiate form. We can see the derivative of x respect to the time equals this equation here. The derivative of y respect to the time equals this equation here. Goal is to estimate alpha, beta, gamma, delta. Yeah, in order to apply PSO, now, of course, as I told you last time, PSO is in the sense basically discrete method, or at least can be seen in form of a discrete method. And we need to realize the discretization of this system here. Before try to explain the discretization, which we can see in its basic concept in this picture here, and probably it makes sense to tell you about the model, just a few words. Lotka-Volterra model is known also as with the name prey-predator model, in which X is the prey, or better to say the number of the preys, and Y represent the number of the predators. Just to understand, just to explain why can be used to describe a prey-predator model, which could be also seen in the context of pandemic, in the sense is also pandemic is in the prey-predator model, because look, just looking at this equation here, why X represent the preys? Yeah, because if no predators, if the number of predators is 0, this element disappears. We have an easy equation that you can recognize from math, assuming that alpha, beta, delta, gamma in this form are positive. We can see that the number, X is the number of the preys, will increase exponentially. I don't know if you remember the solution of this differential equation, if alpha is positive. Of course, this model has some limitation, because we can see here, for instance, some limitation, because even though in an ecosystem, let me say, we don't have predators, of course, the preys, the number of the preys does not increase indefinitely. The preys does not increase until infinite. The reason is that you have other limitations, room limitation, food limitation, which is not, these limitations are not included in the model. We have a more advanced model, of course. In this sense, we can think together in a possible project which consider a more advanced model, which I have, to identify alpha, beta. In this case, in the more advanced models, we have more parameters, but anyway, the parameters of the prey-predator system. We did something similar in an ecosystem fishers, I told you. Why represent, or could model the predators? Look at this. If I don't have a prey, in the dynamics of the predators, please pay attention. What I'm saying is a little bit not exactly precise, because I cannot separate the dynamics. But if X is 0 in one case and Y is 0, we can see that I can speak about prey dynamics and predator dynamics. Look here. If X is 0, here, in the variation of the predators, or in the equation of in the differential equation, we describe the dynamics of the predator. We have just a dynamics which depends on Y, if this is 0. Of course, the model considers the dynamics, let me say, of both, and these two dynamics are interconnected. If this is zero, we can see, assuming that gamma is positive, that the number of the predator is going to zero exponentially. Because in this model here, the predator does not find food in the set. Of course, there's also this limitation because the predator probably somehow will survive different food. It could be, but in this model here is represented in this form. Of course, this element here, the multiplication between x and y, represent the interconnections, which in one case we can see increasing the predator will decrease the number of prey, and here increasing the prey, we will increase the number of predators. I mean, I don't want to go in depth on this, but think about us. Think about us. And therefore, this opposite interconnection, ones with minus, one with plus, generates oscillations. We have seen different codes. Let me now go ahead with the topic of today. But in any case, I introduced this because we can consider in this course a different, more advanced model, and using, for instance, PSO, but other methods which I will introduce, at least one today, can be used, these methods, to identify the parameters which characterizes, the parameters which characterize the model. In this case, alpha, beta, delta, gamma. Therefore, the name parametric identification, because this parameter, alpha, beta, gamma, delta, characterize physically the system, in the sense the model. In the non-parametric identification, the parameters could also be not related to the physical system, in the sense. And we can see here also the stability of the dynamics, again, of the dynamics is really characterized by alpha, beta, delta, gamma. Discretization. Probably you didn't hear about discretization, not yet, no? The first time. Yesterday, probably in the other course. Look this. Here, I introduce the forward-Euler method for discretization. We can see here, and this is a sketch that in red, I try to represent the forward method, and in blue, the backward method. This means it seems to be that from this sketch that I have a forward method, I have a backward method. If I wonder how many methods I have, oh, extremely many. For different reasons, very shortly, because we have really different dynamics. And to choose which one, probably you heard about Runge-Kutta method, Owen method. I don't remember the methods, but we have really many. If you look in MATLAB, you can see how many methods you can use to discretize a continuous system. Because I would like to remember that MATLAB is the numerical methods. And now we have tried to introduce numerical methods in the context of identification, which numerical methods, one method we will see, which use a discretization method to perform to this identification procedure. Look at this moment of the forward-Euler method, which is most used, but not the best one. It depends on the characteristic of the dynamics. I will come back on this forward, backward, and other methods when I will tell you about the controller. At this moment, let me go ahead with identification using the forward-Euler. But if you remember a little bit in gymnasium, and if you look at this scheme here, or at this graph, Probably you remember a little bit that you can approximate a function from the upper part or from the lower part. Just give you the feeling. This is a little bit a possible sketch which can be used to figure out these two different methods, forward and backward. But I will go really in depth when we will do the discrete controller. At this moment, I would like to go ahead with the forward Euler, which is characterized, excuse me, by, let me consider this part of the slide, which is characterized by these equations. First of all, Ts is the sample time, which we can see appear here. And related to this scheme here, we can understand intuitively what Ts here is. Ts is this distance between, well, let me say, the distance between the sample over time. Yeah, of course, it's time. Let me write blue. At this moment, Ts is constant, but could be also variable. But let me fix Ts constant. What this expression says that the actual value, the value of the variable x, in this case, the number of praise is circa, look at this expression here, x of k minus 1 multiply Ts, which for, let me say, practical reason, for nomenclature reasons, are is basically in all literature, in the literature, this nomenclature is simplified in this form here, but Ts is inside. When we apply it with MATLAB or with any kind of software, Ts must be considered, but inside the argument, we can consider something like normalized. But for easy notation, we consider x as a function of k, which is a counter, an integer, we can see here. But the representation of what I am doing is here. Let me consider the red, and I will clarify a little bit the structure of the red approximation, and we will go in depth, consider the difference between red and blue during the semester. Yeah, basically, this is for k, this value is for k equal 1, this value is for k equal 2, and so on, we can see. Typically, as is written here, we omit in our representation Ts. The same for y. Now, very important. What about the derivative? The derivative is approximated in this context. X of k minus of k minus 1 divided Ts. This, I think, I don't need to explain to clarify the meaning, because we did also in gymnasium something like that. Now the difference between two elements, this here and this here, divided Ts. This is exactly the approximation of the derivative which we learned in high school. Of course, this notation here means x of k Ts, and here means x of k minus 1 in parentheses multiply Ts, but we didn't put basically. I can do the same. I can do the same for y. I didn't put here, but I put here directly in the application. Before explaining the discretization of the system, which is here, the applications I told you, I would like to give you just one indication of about the difference between backward and forward. The basic difference is not in the way to approximate the derivative, but what I am considering as actual value. I mean, in forward, we will consider xt circa x of tk minus 1 multiplied ts, or x of k minus 1 in an easy form. In backward, we will consider x of k. This means formally the derivatives are the same, but with different meaning. Because if you consider forward is the approximation of the derivative in forward way, because if this is the actual way, the actual value, this is the future. Or if you don't like to speak about the future, if this is the past, this is the present. This means I approximate the derivative looking forward. But as I told you, if instead of this expression here, or that this one, I will consider xk, I will look back. I mean, in order to approximate, I mean, here, to approximate the derivative, I look forward. And in the blue, I am here, and I look back. Basically, it's in a different reference point to approximate the derivative. Of course, we will go in depth in the future. We have a question, but I don't know the future. Yeah, but we assume to know that in order to build the model in a formal way, basically, I didn't put here the derivative of y, but it's the same like here, just to replace x and y, x with y. And then I plug in all this information here, or approximation information in this sense. And I will obtain these two equations, which represent, these two equations represent the discretized system this here. Now, from here to here is an easy matter, because I multiply by TS, I bring this element on the right part, I will obtain through easy calculations, algebraic calculation, from these two equations, these two here. Now, it doesn't matter if I don't have the future. As I told you, this calculation here, or the disposition here, calculation, this sense, or position, better to say, this assumption, is formal assumption, which allows, once I plug in all these assumptions, including the derivative of y, which I didn't put here, I will obtain at the end of the calculations these two equations, which can be also in more compact form. It can be written in more compact form than these two equations here, but you can consider this, doesn't matter. These two equations are equivalent to this one. Now, it doesn't matter if the future, I don't know, because the future I never know. Basically, I have two equations which can be used to predict the future. Because in any case, we have on the right part, assume in accordance with this method here, in accordance with this method, forward Euler, other method is not so, let me say, flexible. We can see that I can separate the present with the future, or if you'd like to speak about the future, the past with the present. But let me speak about the future in both equations. This means I can use this formal way to represent the system to predict the future. I don't see any contradiction now. Assuming that I know the future, but of course, just formally to put my condition, let me say, now I have two equations which allow to say I can predict what happens, let me say, tomorrow. If I know what happens, what I have today for x and y, because k minus 1 represent today. Assuming that TS is done, assuming that I am able to identify, oh, I know alpha, beta, gamma, delta. I don't see delta, probably we have an error here. Let me correct. This is gamma. Okay, this is delta. I see the error. Let me correct. Yeah. Here was correct, and here I made a mistake, but it's not so heavy. Now, how I can estimate alpha, beta, gamma, delta, which characterize really the system? Because assuming that I can measure x and y, in particular x k minus 1 and y k minus 1, is the actual value of my state variables. In our case, prey and predators, number of prey and predators. But the problem is, yes, I know each day I can consider this information on the right to predict what will be tomorrow in terms of number of prey, in terms of number of predator. But of course, I have to assume that I know alpha, beta, gamma, and delta. Otherwise, I cannot predict, or I can predict with larger uncertainties. As I told you, the future states. I will upload this slide in my study. Here, I have a calculation of a equilibrium point, or the point, which I don't want to go really in depth because it's not the topic of today. Because today we try to go in depth on identification, dynamical identification, but a few words because you will find the slide in my study. And again, in order to explain quickly what the equilibrium points are, I would like to say that a nonlinear system is characterized by equilibrium points. We can see the definition of the equilibrium points here. Basically means that no changes. Basically, the dynamics we have a static dynamics. I mean, if xk equal xk minus 1, we don't have that x does not change for xk. No? If this holds for xk, that means the number of the preys does not change, and the number of the predator does not change. It's interesting in the analysis of dynamical system to find this kind of point, which is characterized by no dynamics, let me say, no? Because if for each k, xk equals xk minus 1 and yk equals yk minus 1, this means equilibrium point or equilibrium points could be more than 1 because no changes in the number of uh, the preys and predators. Now, if I consider these two positions in my two equations, I can, for instance, for the first equation, I can cancel this with this because I assume it as to say, I do some calculations and I will obtain this equilibrium point, yk minus 1 equals yk equals alpha divided beta. Look a little bit at home. I don't want to go in depth on this. If I do the same, considering yk equal yk minus 1, I will obtain these two this condition here. We can see that the equilibrium point depends alpha, beta, gamma. Yeah, probably I have mistakes. Yeah, seems to be. Let me see, because I forgot delta here. Yeah, the error is here. Let me see. Yeah, again, let me correct for you. Excuse me for this error. This means something like that, I hope. Let me check again because I don't want to upload. Yeah, because this was delta. once I correct it, yeah. Yeah. This means this is delta. We can see that the equilibrium points depends on these parameters. This means also another reasons to identify this correctly or more precisely this parameter, because the equilibrium points are extremely important in control, because to control a system around an equilibrium point, we can understand very well, easier than control the system far away from this equilibrium point. This means if x equal this value and y equal this value, we have an ecosystem which basically is in equilibrium. This means I don't risk that the prey will extinguish. I don't risk that the predator will extinguish. This means to control around this two value, these two number of predators, number of prey, is extremely easy, more easy than to control far away. I would like to. I don't have here, but next time I will bring. I don't have. Let me see if I find. Let me see if I find a slide for you in order to show you in a technical system. 1 second. Yeah, I have it here. I think I found it. Let me share this document in order to show you in a technical. I don't know if it's visible. I think so. I am not able to move the inverse pendulum. Yeah. Look at the scheme here. Definition of equilibrium points. I don't want to go in depth, just to clarify how is important, how the equilibrium point is important. Look, here we can demonstrate that this is an equilibrium point, and also this one in the vertical position, once down, once up, we have two equilibrium points. And this point here is not an equilibrium point, because if I have this point here as initial point, of course, the pendulum will reach this point here because of the presence of the gravitational force. Now we can also demonstrate that this equilibrium point, it's intuitive in this case, is a stable one. Better to say is asymptotically stable. And this equilibrium point is unstable. This means if I move a little bit from this equilibrium point, I will fall down in this one. Now, the analysis of the equilibrium points we can understand from this example here in the nonlinear systems is extremely important, because it's clear that to control the system in this position here, the pendulum in the system here, is easier than to control in the system here, because the system here is for each nature asymptotically stable. This means I cannot do basically anything to achieve this point here. Of course, if I have achieved with particular specification in time, I have to implement a controller. But in any case, to maintain in a vertical position is extremely more difficult than in this one. But maintain this position here is more difficult, is more also cost more in terms of energy, also with respect to this one, because here I have to overcome the maximum moment. I mean, this position here is not an equilibrium point. In order to understand better the context, the idea of the equilibrium point, allow me to mimic. If I have a pendulum, excuse me, this. Of course, this position here should be easy to be controlled. Basically, if I don't have specification in time, I cannot do anything. This is a little bit more difficult because we have in the lab. It's clear that if I disturb, the risk that I fell down. This means I have to do something. But the more difficult position to be controlled is one. We can see far away from both, because this position here, to be maintained, the system in this position, here I have to overcome the maximum moment. Let me come back on our system here. I don't have time now to tell you about it's not the topic of today. When an equilibrium point is stable, when an equilibrium point is asymptotically stable, when an equilibrium point is unstable, but we can do eventually together in the project. It depends on the Jacobian. Probably this concept I already told you in the different tools in modeling or dynamical systems. I don't remember where. But very important for today to notice that the equilibrium points, or this equilibrium point, this here, which I have, depend on the parameters. This means we have a reason more to identify in a precise way alpha, beta, gamma, delta. We can see that we have another equilibrium point, but it seems to be trivial, but it's not. At 0, 0. I mean, if no prey is not predator, of course, the system remains at 0, but it's not totally correct what I am saying. 0 is trivial because if you put here 0 everywhere, we have 0 everywhere. No? If xk equal xk minus 1 equals 0, we have 0 equals 0 both. Why it is not trivial? I don't have time to tell you that. Because mathematically, if y is 0, but x is not exactly 0, of course, it's an equilibrium point, but it's unstable equilibrium point. In this sense, it's not a trivial equilibrium point. It seems to be okay if I don't have prey, if I don't have predators. Of course, it's an equilibrium point, and it seems to be stable, but it's not. Or asymptotically stable. It's unstable because if y is 0 and x is not 0, in accordance with this mathematical model, I told you before, no? We have something which is exponentially increasing. Exactly what we can see here. But anyway, about the dynamics today, I don't want to go ahead. Let me go ahead with the lecture of today, so we can see the structure of a possible identification frame, and then I try to link with what we did last week, and I try to introduce what I will do next week, also using a simulation, but of course for a system a little bit didactic, a little bit easier, I would like to say. But anyway, I have also simulations for this kind of system. We did also a publication in a course using PSO and using also different methods. With Lotka Volterra once, and another publication with SIR. But let me come back. Equilibrium points I sketched because you can find this slide in my study, but not only. I try to emphasize how the equilibrium point depends on the parameter. This means to identify properly, in the best way, let me say, the parameter allow to identify the equilibrium points. The equilibrium points are important in control. or in any case, to analyze the system, because again, here, let me say, with this number of predators, with this number of preys, with the number of predators, with the number of preys, we have an ecosystem which guarantees the equilibrium. This means no risk to extinguish preys, no risk to extinguish predators. Do you remember last time, so today I repeat it, I told you about the regressor, the exponential regressor, which I used to fit the data. Now, when we have a dynamical system, and of course, we have a system, we have measurements, and we have a model. This means we have a dynamical system with a model. The regressor, please pay attention to this point here. The regressor is represented by the model. Therefore, also, I don't remember of today I used the word model, but last time I used the word model. A regressor isn't a function. The regressor is a model somehow. Now, here we have a model which is dynamics in discrete form, because we can see that xk is a function of xk minus 1, and yk is a function of y of k minus 1. Y of k is a function y of k is a function of y of k minus 1. Of course, we have alpha, beta, gamma, delta, which must be let me say, identified. But anyway, as a variable, we have this dependence. Now, why this is the regressor somehow? It's the regressor because as today, instead of exponential function as a function of x, we have a function of x, and a little bit more complex because we have a function of x and y, but we have two equations. But the idea is to show you that in our case, the regressor is, or these two equations represent the regressor. If you think about the expression of today, which I repeated today, we have, I remember, y bereknet, something like that, equals an exponential function which depends on x, which is fixed, which is the data which I measure. But here we don't have exponential function, but we can also consider model with exponential function. We have nevertheless a function of x and y in particular, and because a little bit more complex. But in any case, in a function. The difference in here that we have a dynamic structure. We don't have k and k, we have k and k minus 1. But in any case, in a function, which depends on parameter alpha, beta. Today, we have seen our parameter was x1, x2, and x3. But the idea is to show you the analogy. Of course, here is a little bit more complex. We try to go also ahead because we have two equations. The parameters, better to say, the regressor is represented by the system of these two equations. Until now, we have seen just one equation. But in any case, we have x, the equation of today in the morning. We have the parameters x1 and x2 and x3. And here we have x and y as variable. And we have also measurement in x and y. And as before, as in the regressor of today, we have a parameter to be estimated, alpha, in this case, alpha, beta, gamma, delta, 4 parameters instead of 3. Of course, the system is a little bit more complex. We speak about a regressor which consists of two equations, dynamic equation. But now let me go ahead in order to emphasize again the analogy, and then we can understand how I can nevertheless apply PSO and also other methods. About the other method, we will go in depth next week. I will show you one method. Look, again, we can see in this frame, the goal is to identify, to estimate. Estimation is used in synonymous for identify. Identifies is more general. Estimation typically, with estimation, we consider an optimal identification. alpha, beta, gamma, delta. As today or the last time, when the goal was to estimate or to identify, if you like, x1, x2, and x3. Of course, here the system is more complex, but can be nevertheless applied PSO. Look what we can do. A little bit, let me show you slowly, because the information is a little bit structured, but not difficult. I hope I have all material. Let me see. Yeah, I have everything. Look what we can do. I can write here the first equation again. Let's consider that I can measure x and y. This means this I know, this I know, this I know, this I know. I can repeat again the equation for y. Basically, these two equations are these two equations. Then, what I am doing, I will consider xk plus 1 formally. Basically, I will add 1 everywhere. I will obtain this equation here, and I will obtain for y this equation here. Clear? Formally, just for. And I will do for windows with length m. Look. Basically, I will consider m element for x and for y. Clear? What I'm doing. But if you think about, now let me go ahead and then I will try to compare. Here is clear. No? I will consider in a set of probably could be see a little bit better on the right part. I have let me say elements on x and y, and I can organize the data in this form here. This means now, look what I am doing now. If I am considering now x of k minus f of k minus 1, this means this minus this minus this minus this minus this, basically for all element which I have, I can rewrite everything which I have here. I did a little bit quickly, but we can understand what I am doing. Basically, I have a vector, is a vector on the right part, left part, let me say, which way, and on the right part, I will have basically a matrix which multiply by TS, because TS is everywhere. We can see here, TS is everywhere, which multiply something which can be expressed, we can see here, can be expressed as a matrix which multiply alpha, beta, gamma, delta, which are my parameter, which must be, but should be estimated. I don't know if it's, I can repeat a little bit this way to represent this data, this way to represent this data. I think it's not difficult to see how from here I can write this column here, because it's this minus this minus this minus this, and so on until m, let me say, until m, and then I formalize in a column. Once I formalize in a column, I can see what is on the right part as TS, which multiply everything, because TS is a common parameter. But what is the everything? I can here, let me say, put in evidence in the vector theta, alpha, beta, gamma, delta. And of course, this matrix here, multiply this vector here, we will generate this information here. We can check. Look, xk minus 1 is multiplied by alpha. This here is multiplied, this element here is multiplied by beta. TS is everywhere. No? We can see from here. Now, this window of element must be measured. This matrix, of course, must be given through the measurements. Now, to obtain the measurements, what we can do, we can consider k plus m, the actual, let me say here, the actual value, and k plus m minus 1, the previous value, until k. This means the old value is k, and the new value is k plus m. Because as I told you at the beginning, we don't know the future. We cannot go to the future. This is just a way to represent. This is a way to represent in which k plus m represent the actual value. K plus m minus 1, the previous value, and the oldest value, x, is represented by k, x of k. This means once we have this vector, and we have this matrix, of course, we can calculate alpha, beta, gamma, delta. We will see, nevertheless, next week how we can, using the least square, and in particular, the recursive least square, I will try to emphasize the difference between least square and recursive least square. I have a course in optimization in which I go more in depth, but in any case, I will do an example in order to, of course, to understand better. I will show you that this is the solution. This is the solution in a static way, and in dynamical way. We can, starting from this solution, to obtain something more suitable. Now, to conclude this part here, and to show you how we can basically use PSO in this context. Yeah, there is it's not so difficult to think that coming back to this form here, without putting in this form, which we will see next week in the context of recursive least square. At the beginning, I will show you very shortly something in static least square. We can use, nevertheless, PSO, because we have here, as I told you before, a regressor. We have the set of value x and y. This means we can build the program as last time, in which if I given in a window for x and y, if you want, we can use also this window here, but you don't need it. You don't need it, this. As in the formal, let me say, least square, because you can use directly, as we did last time, the regressor and the vector x, of course, calculated within a window in the past, and then the vector y, calculate again as the window in the past. And then we can run the PSO with minimizing the cost function, which could be also, we have seen today again, the least square. The only thing which you have to be careful, we will see probably a bit better in the future, that this window is a window with shift over time. I mean, it's not fixed, but it shift over time because we can see the regressor dynamics. Is dynamic. The regressor has no dynamics. This means I will move the window of the data in order to estimate over time alpha, beta, gamma, delta, alpha, beta, gamma, delta. I don't know if we can see a little bit this idea without implementing. In order to simplify, in order to clarify a little bit better, if you consider just one equation, if you consider just one equation, let me consider also just the dynamic of X. This means now we can probably see a little bit better what I intend, because this equation here is exactly now equivalent to our exponential function. The exponential function which I repeated today, which we have just in this case, just in the parameter to be somehow to be estimated. I don't know if it's possible. This is possible to see it. We measure xk minus 1 and xk. Let me see if I can say something more about that. Of course, we measure more than two values, no? As we have seen so last time. X data, you remember, Y data is in a long set of data. I mean, if I have xk and xk minus 1, I don't need to optimize because alpha is calculated directly. If I have xk minus 1, alpha is calculated directly. But this is not the case. We have many value of x. If you like, you can consider, as I told you, xk minus k minus 1. Basically, we try to find a compromise for alpha using PSO, which minimize the cost function, which could be, for instance, the least square. Why not? Let me clarify this concept that we will close for today. Let me do a static example in order to show you that why I need a window, and the window is the window with shift over time. This does not necessarily imply that alpha change over time. Could be also after the transient constant. That depends. I told you next time why. But let me show you what I intend. It's in an easy example. How we can express this? Yeah. A trivial example. It seems to be in a contradiction. Y1 equals A multiplied X1, y2 equals a multiply x2. We don't have an a which satisfies both. It's clear. But we can find an approximation. If you remember in the lecture of optimization, I did the example. This is the sense. The mean value between y1 and y2. This is A. I don't know if you remember. This is a little bit the sense that I can nevertheless use PSO in the context of optimization, which I can choose, for instance, least square, why not, but another method. But the regressor is exactly, if you consider this example here, the equation. Of course, here is a little bit more complex because we have two equations. If you want, you can use as this is vector a possible method, but it's not necessarily. And the PSO, we will find alpha, beta, delta, gamma, minimizing Snekos function. If you want, we can look together the application of PSO. If you want to work with this. Let me go. If you want to apply, let me see this this method in your projects. I have implemented many times, but didactically a little bit complex. Nevertheless, if I find we can see together the software. But you understand that, of course, it's not much different because nevertheless we have a regressor with dependence of parameter alpha, beta, gamma, delta. Of course, we have a window which is shift over time because the system is now characterized in dynamical way. This we will see next week a little bit more in depth. Does not mean that alpha, beta, gamma, delta necessarily depends of time. It's variable time, of course, possibly. But if the model is quite let me say good, it depends just a little bit. We will go in depth next week, but using the recursively square, starting from this consideration. For PSO, if you want to do something in this direction, we can do together probably my lab. I can show you, but I think I sketch what we can do because the regress is there. The regress is the model. Also, last time we had a model. Now it's more connected with the dynamics. Okay, I will stop now to record.